Hello, and welcome to the first video in this playlist for laser welding. Before we start, let's go and share the screen so you can follow along with the PowerPoint that I'm going to use. My name is Girish Kelkar, and I am a welding consultant and working as WJM Technologies, which stands for Welding and Joining of Materials. Today, we're going to talk about fundamentals of laser welding, trying to understand how do we use laser energy to create a molten metal puddle. To understand that, first we need to understand the difference between regular light and laser light. As I've shown in the schematic on the right, ordinary light has photons of many wavelengths, and they are often not traveling in the same direction. They are not parallel. This is obvious from looking at the light coming out from a light bulb or a tube light. Laser light, in contrast, is monochromatic. That means all the photons coming out from the laser have the same wavelength. Also, this laser light is collimated. That means all the photons are traveling pretty much in the same direction. There are other properties of light which are of importance in other processing technologies, but not for welding. Polarization is one, but it doesn't affect welding as much, but it can affect laser cutting with CO2 lasers. Another property is coherence, where the photons are in phase, which is also not a property which is very required or useful for welding. So as far as welding and most of the materials processing is concerned, we are interested in monochromatic and collimated behavior. How does that help? When we shine a laser light on a lens, because the light is monochromatic and collimated, it focuses down to a very small spot size. Now, that spot size can be of the order of 10 to 500 microns for welding, usually in the range of, say, 20 to 200 microns. On the other hand, ordinary light, because it has many wavelengths and not exactly parallel, can focus down to a much bigger spot, which does not have enough energy density for materials processing. Here is a setup for laser. There's a laser, there's a collimating lens, a mirror, a focus lens, and a workpiece. Once I click, you should start seeing a red light beam going from the laser all the way to the workpiece. Let's see how this works. There you can see the beam going down, focus is down. So one of the interesting properties of laser light is when the light comes out from a solid medium, such as a glass or a ceramic where the laser light is generated, into air, it has a slight divergence. So even though the beam is pretty straight, it still has a slight divergence. So first thing we have to do is take that laser beam and put it into a collimating lens to make it parallel again. Then, depending on the configuration of the laser, you may have a mirror which deflects the beam down into a focus lens, and the focus lens focuses it down to a small spot size. The distance between the focus lens and the workpiece is called the focal length of the lens. There might be an opportunity to see the welding in progress through a stereo microscope or through a camera. In either case, the viewer is protected from the laser light by the right amount of coatings on the stereo microscope lenses. Another way to deliver the laser light is through a fiber. So there's a laser shown in the box over here. The energy can be transported through a fiber into a focus head. Again, the fiber is made of glass. So when the light emerges from the fiber, it is slightly diverging and it has to be collimated. Then it has to be focused down to a small spot size. This arrangement of collimating lens and focus lens is present in all laser welding configurations. This over here is called the focus head. There are certain wavelengths of light which can travel through fiber or through air, which includes the 1 micron laser light and lower wavelengths. However, the larger wavelength, the 10 microns, cannot travel through a fiber. and can only be transported through air. How the energy is absorbed by various metals. On this chart, we see on the vertical axis we have reflectivity, on the horizontal axis we have wavelength. So we have the CO2 laser at 10 microns. 1 micron is YAG or fiber or disc lasers. There's a green laser at about 0.55 and a blue laser close to 0.4 micron. On this chart, we can see the reflectivity changes as a function of wavelength for different metals. We see that for silver is a good reflector for all lights, whether it's infrared or green or blue. And that is quite obvious from the fact that silver is a white metal, and hence it actually means that it's going to reflect everything. Copper, on the other hand, has slightly interesting behavior. Copper is reddish in color, so it tends to actively reflect the 1 micron light. But once you go into green and blue, the absorption is pretty good. So copper has a significant change in absorption as we go from 1 micron to green to blue. And there is a reason why blue lasers are going to become popular for welding copper. Keep in mind that this chart is shown for reflectivity, or the other way around, looking at it is absorption at room temperature. So one of the benefits, one of the interesting aspects of lasers is that the absorption actually changes very quickly with temperature. And that makes it possible for us to use various wavelengths, even though the initial absorption may not be good. How does that work? Let's look at in the next slide. I'm showing you schematically a chart where we have absorption on the vertical axis and temperature on the horizontal axis. Let's say we are welding copper or say silver, where the initial absorption is very low, say around 10 or 15%. When the laser light initially strikes the surface of copper, the absorption is low. That means the rest of the energy is being reflected. However, the small amount that is absorbed, say 10 or 15 or 20%, that is converted to temperature. So there's a slight temperature rise in the region where the laser energy is shining on the surface. As the temperature increases, the absorptivity for that particular wavelength increases. So as the temperature goes up, the absorption goes up. So the next wave of photons which are coming down, those are absorbed better than the previous wave. And then what happens is the temperature rises even further. So this ends up in a chain reaction, which results in very rapid rise in temperature, which eventually leads to melting, which is required for welding. So this phenomena, this chain reaction, makes it possible for wavelengths to be absorbed and have a practical result of melting, even though the initial absorption could be quite low. So as long as we have enough number of photons hitting the surface, enough energy density on the surface, we can actually melt practically any metal because of this chain reaction process. So this is a very important phenomena that makes it possible for laser welding. So in summary, laser light is monochromatic and collimated, and hence we can focus it down to a very small spot with high energy density. That means photons per unit area. Based on wavelength, material properties, and energy density, the part surfaces can be made to absorb light in substantial quantity. And that is required because we want to have an increase in temperature, very rapid increase in temperature at the welding location. Surface absorption and increase in temperature sets up a chain reaction which leads to rapid melting of materials. Given that, in this process of chain reaction, we can now produce melting in a fraction of a millisecond. So within a half a millisecond or less, we can actually initiate melting on the surface. Keep in mind that there are many other aspects of laser welding, including design, process, metallurgy, which we will be reviewing in other videos posted in this playlist. So in this particular video, we were focusing on how and the fundamental reason why we can use a laser beam to create melting of materials. Thank you. If you're interested in learning more about welding and joining, please do subscribe to this YouTube channel. And you can find other videos on other topics, including laser welding, in the different playlists below. Looking forward to keeping in touch and enjoy this YouTube channel. Thank you.